This is lecture 5 of Logika računalništvu, logic in computer science. Last week we introduced the language of predicate logic, that is how we build formulas of predicate logic, and we extended the natural deduction proof system, which we'd previously used for propositional logic, to work with predicate logic by giving additional rules for the universal and existential quantifier, and also for the equality predicate. Now, when we looked at natural deduction for propositional logic, we followed that up with two theorems that explained that the natural deduction rules are indeed a good set of rules for propositional logic. That was the soundness and completeness theorems. The soundness theorem said that if we can prove something in natural deduction, then it is indeed a valid formula. And the completeness theorem said that not only that, but also if we have a valid formula, then we can find a proof of it. In fact, those results extend to predicate logic, but it is not quite so easy to formulate them in predicate logic, because the difficulty is in explaining what it means for a formula of predicate logic to be valid. In order to do that, we have to say how we understand the meaning of formulas, and that is a lot more complicated than in the case of propositional logic. So in propositional logic, all we had to do was to assign truth values to the propositional atoms, and from that it was easy to derive a truth value for a propositional formula that involved those propositional atoms. The structure of the formulas of predicate logic is much more complicated, and so understanding the circumstances in which they are true or false is going to involve introducing some new material in order to cover that case. So I'm going to first introduce the mathematical definitions we need in order to understand the meaning of predicate logic formulas. And what this relies on is something called a structure. Let's write that down, a structure. Which actually in the course textbook is called a model in the Huth and Ryan textbook. So I prefer the term structure as the official structure because in proper courses on mathematical logic there's a distinction between structure and model. But for the purposes of this course we will blur that distinction a little bit, and so we won't worry too much, and I may sometimes refer to structures and sometimes to models. But in any case, the important thing is not really what the definition is called, it's what it is. So let me just give you the abstract definition first, and then we'll look at some examples. So a structure, so what it is, it's so we need what a structure is depends on the signature we're working with. So you will remember from last week that in order to build the language of formulas we need a signature, and the signature gave us the collection of predicate symbols and the collection of function symbols that we use to build terms and formulas. So a structure, let's say a structure for a signature curly p curly f. So curly p is a collection of predicate symbols, curly f is the collection of function symbols, it's a mathematical structure. So mathematical structure means some data, like for a group. So a group is a set with an identity element and a multiplication operating on it, satisfying certain principles. So we're going to be more abstract than that, but it's quite similar. So we call the whole structure itself curly M. This is a particular structure, and curly M is going to be, it consists of a set, a collection of mathematical objects that are going to interpret the predicate symbols. I'm just going to write the notation down now, and that's a curly P, and a collection of other mathematical objects here. It all looks rather mysterious at the moment. But let me explain what we're doing. So here, this is a set. So M is a set. In fact, we'll ask for it to be non-empty. So it's at least a little bit interesting. So M is a non-empty set. It's sometimes called the underlying set. Of the structure, the underlying set of the constructor, or also sometimes the universe of the structure. So I should have said underlying set of the structure, or the universe. And what we have here is a collection for every predicate symbol P in the collection of all predicate symbols that we've got in our signature. What we have is a mathematical function, P superscript M, which we read as the interpretation of the predicate symbol P in the structure M. And this is a function from So what this means is the set of arity P tuples of M. So the set, so if the arity P was 2, this would be M squared. That's the set of all ordered pairs of elements coming from M. If arity of P was 1, it would be just the set of single elements coming from M, and so on. If arity P was, if P was a 3, if P was an arity 3 predicate symbol, then this would be the set of all triples of elements coming from M. And the point is, this tells us when such a tuple, such a two-element pair or a triple or a quadruple, depending on the arity of P, when it's true or false. So it maps that to true and to false, to that set. And the function symbol, so again, we have an interpretation of every predicate symbol and an interpretation of every function symbol. So for every function symbol in the collection curly f little, so every function symbol little f in the collection curly f of all function symbols in the signature, we also have an interpretation f superscript m. So the interpretation of the function symbol f in the structure M is again a function that again takes oops, it should be the arity of f now, takes as many arguments from the underlying set as its arity. And this time, because it's a function symbol, it gives us back an element again of the underlying set M. Okay, and that's what a structure is. So as I say, it looks very mysterious at the moment. So let's expand it with some examples. So let's go on to a fresh page for that. Or maybe let's continue the same page. So let's consider examples for the signature we considered last week, where we had less than equal relation as a binary predicate, so that's one with two arguments. So this symbol has a two-argument predicate, and we had constants for 0 and 1. So remember, those are zero argument, zero arity function symbols, those constants, and for plus for addition and multiplication. So this was the signature of a semi-ring. So the example structures for this signature. And the point is of a structure gives one mathematical environment in which we can interpret the language of predicate logic involving these symbols here. So we certainly know that one place we can interpret this language is in the natural numbers, and that structure would be, so the underlying set would be, well, let's give the structure itself a name. So why not call it, let's call it kind of curly n. So this would have underlying set natural numbers, underlying an interpretation less than equals in the natural numbers, and interpretations of 0 in the natural numbers, 1 in the natural numbers, plus in the natural numbers, and times in the natural numbers. And then, to specify what these mean, we need to define the function from the underlying set with the right arity. So from tuples from the underlying set with the right arity to true and false in the case of less than equals, and appropriate functions from the underlying set to itself in the case of the function symbols. And that's easily done because so we just take the natural interpretations. So less than equals in the natural numbers when applied to natural numbers x and y. We will just define that to be equal to, so it's we're interpreting the less than equal symbol in the natural numbers. The arity of the less than equal symbol is 2, so it expects a pair of arguments from the underlying set, which is here, which is the natural numbers, and it will map any such pair of arguments to either true or false. So we simply do the natural thing. We say that this is true if, in the case that x is less than equal to y, and false if x is not less than or equal to y, which means y is less than x. So let's just pause a little bit to say how the relation less than equals appears in different ways here. So this here is just a symbol we've given ourselves in our signature, a predicate symbol that we use to build formulas with. We could, if we had wanted to, we could have named it Fred. It doesn't matter what we call it, we just need a binary relation symbol that we're going to use. It's only here when we define a structure for it that we give it a meaning. So here now we're defining, so this less than equals is the symbol, the predicate symbol we use, which would be Fred if we'd called it Fred. But in this case, we've called it less than equals because that's more natural from a mathematical point of view. And we put this in the structure n superscript on to say, here, this is the function we're defining that will interpret this predicate symbol. This function expects 2 arguments because the arity of the less than equal symbol is 2. So we give it 2 arguments. These x and y are natural numbers. And the result of the function is either true if now the natural number x is less than equal to y. So here we are using the standard less than equals relation on the natural numbers. And here it's false if y, the natural number y, is less than x. So these are the standard relations on the natural numbers, the order relations on the natural numbers. Of course, in the end, we're defining it in such a way that this is also the standard order relation on the natural numbers. But that's our choice. We're choosing to interpret it in this structure. Another structure would be, we could also do, well, actually, let's finish the structure. So the same way, so 0, interpretation of 0 in n. So 0 is a constant, so that's a function symbol of arity 0. So it expects no arguments. So we need to define a function that takes no arguments. So we could either do that in the programming language way and give it an open and closed brackets as its argument, or we could just say, well, expecting no arguments is just like defining a constant, so we'll do the latter. We won't bother with the open and closed brackets, and we'll say this is interpreted as the natural number 0. So here, again, this 0 is the function symbol, which is a constant because it has arity 0 in the signature. So that's just something, some piece of syntax that we use in building up formulas. This 0 superscript n is the 0 in it is again the function symbol, the piece of syntax, but we're now saying we're interpreting this function symbol in the signature in the structure n, and that is interpreted as an element, in this case, of the underlying set because it's a function symbol of arity, it's a function of arity 0, so it takes no arguments, so that's just like giving an element of the natural numbers n, and that element is the actual natural number 0. Once again, we could have defined it to be any natural number. We could have taken 17 or something, but we have chosen what the natural interpretation here suggested by the syntax 0. So in the same way, we need to define the interpretation of 1. Well, that will be 1. Interpretation of plus in the additional symbol in n. So again, that's got arity 2, so it expects 2 arguments, which are natural numbers. And again, it's a function symbol, so the function symbols map into the underlying set, so we need to give a natural number as a result, and we just map this to the natural number obtained by adding x and y. So again, plus here, plus in the signature, rather, is just a piece of syntax. We could have called it plus plus. We could have called it Frida, but we've written the plus symbol for it, so just a piece of syntax. The superscript n means the interpretation in the structure n. This is now a mathematical function. It takes 2 arguments. These are natural numbers. Needs to be a natural number. So here on the right, we're using the actual addition operation on the natural numbers. So again, we are defining the meaning of the function symbol plus in the signature to be addition on the natural numbers, but we could have defined it to be any other operation. And times the multiplication in n, of course, the natural interpretation is, again, because we have a natural multiplication operation, is going to be x times y. Okay, so that's one example structure. Another, see how much space we've got. So another example structure would be, let's put a line down here. So another example structure would be, say, a different interpretation in the natural numbers. So it's going to be, still going to have the underlying set as the natural numbers. But the point of this, and we'll have a less than equals n prime and a 0 n prime, 1 n prime, plus n prime, multiplication in n prime, and so on. The point of this example is to say that to give a structure interpreting the syntax, doesn't matter what we choose. A structure can be, as long as the structure interprets the predicate symbols in this way and the function symbols in this way, then that's a perfectly legitimate structure. We don't know what the syntax means until we give it a structure. So if we'd called less than equals Fred and we'd called 0 Frida and so on, we'd have no idea what the interpretation what the symbols are supposed to mean. And really, we don't know what the symbols mean in logic. Logic doesn't know what the symbols mean until you provide a structure. So I'm going to provide another structure, which is a very unintuitive one, because let's just be totally random about this. So the interpretation of less than equals in n prime when applied to two natural numbers x and y is, let's say, true when x is different from y and false when x equals y. Of course, this doesn't satisfy the properties of an order relation, but it doesn't need to. I mean, we just have an arbitrary predicate symbol here. So let's make the interpretation of 0 in n prime 17. The interpretation of 1 in n prime, well, I like the number 17, so let's make that 17 as well. And let's, for the sake of perversity, interpret the addition symbol in n prime to mean multiplication, and the multiplication symbol in n prime, well, we could say to be addition, but let's take something different. So this is multiplication, n dot x dot y. So let's make this, I was going to do subtraction, but actually subtraction's not defined on the natural numbers if y is greater than equal to, if y is greater than x. So, whoops. So let's, oh dear. Whoops. Lost control of my pen. So anyway, we can just take anything arbitrary. So let's say x plus 2 to the y or something like that. It can be completely arbitrary. The point is, so the point of this rather silly interpretation is just that to give a structure, you can choose however you want to interpret the symbols, as long as your predicate interpretations and function interpretations respect the arity. So another more natural structure would be what we might call, so let's draw a line under this. What we might call curly R. And let's make the underlying set of curly R the real numbers. So now we need to have less than equals in curly R. And 0 in the structure are the interpretations of 0, 1 plus and times in the structure R, curly R. So the only thing so here we've just changed the set from the natural numbers to the reals. And so again, we need to specify the less than equals relation, and let's give it, again, this time the natural interpretation. So we say that the interpretation of the less than equals relation when applied to x, y, this is going to be, again, true if now the real number x, because x and y are taken from the underlying set, that's now the set of real numbers. So true if the real number x is less than or equal to the real number y, and false if y is less than or equal to x, and so on with interpreting the function symbols. So let's give it, as I said, the natural interpretation. So the constant 0 in the structure R is going to be interpreted as the real number 0, and so on. Let's just write etc. or dot dot dot. So somehow the point is to give different examples, some natural, some not natural, but they have underlying sets. But in each case, we just need to choose a set and choose an interpretation of the symbols. And of course, depending how we interpret the language in a structure, so for different structures, different formulas are going to, if we interpret, the same formula in different structures, it might have different truth values. So for example, the formula saying that 2, as I think we did last week, that 2 has a square root in the structure, that will be true in the real numbers structure R, but false in the natural numbers structure N, curly N. Okay, so that's the idea of a structure, and the point is that when we have a structure, that determines, the structure is enough to determine whether a sentence is true or false. So when we have a sentence, remember a sentence was a formula over the signature in which all variables are bound by quantifiers. When we have a sentence and we have a structure, we can look at whether the sentence is true. It makes sense to ask, is the sentence true or false in the structure? And it will have exactly one determined truth value. Before moving on, I just want to mention one little difference with the textbook. So in the textbook, the interpretation of predicates is not a function from the arity of the predicate symbol to truth values. It's rather a subset. So they probably don't use the superscript notation as well. I forgot to check on that. I like this superscript notation, but for me then, so my notation, we would have the interpretation, their way of interpreting a predicate symbol in a structure M, they call it a model, as I said, would be as a subset of tuples from the underlying set of the appropriate arity. But this is equivalent. It's a slightly different way of formulating it, but it's equivalent to what we have above. Because any function, that should be round brackets. Because any function to truth values determines a subset, namely the subset of all elements that get mapped to true by the function, and every subset in the same way determines a function to truth values, where you map elements in the subset to true and elements outside the subset to false. I don't want to dwell on this, but you can think about it for yourself. I'm going to stick to my formulation, and the point is, once we've got a structure, we can say what the interpretation of formulas in a structure is. So to do that, we're going to define a relation between a structure and a formula. Or between structures and formulas over the same signature. So this is called the satisfaction relation. And this is a very important relation in logic. And in order to define it, well, ultimately what we're going to be interested in is the case in which phi is a sentence, in which case this relation will either be true, meaning that phi is true in the structure, or false, meaning that phi is false in the structure. But in order to define the relation for sentences, it will prove necessary to define the relation also for formulas that do have free variables. So more generally, we're going to have to define this relation for formulas that have free variables. And to do that, we need to decorate the relation with some information on what the free variables mean. And we decorate it with something called an environment. And traditionally, the Greek letter, lowercase letter rho, is used for environment. So this looks a bit like a P, but it's a Greek lowercase rho, R-H-O. So this is sort of like that or something. Okay, so we're going to define this, and we're going to see why we need this environment when we define it. So where M is a structure, M is a structure, phi a formula, both over the same signature, but I won't write that down, so they both use the same vocabulary of predicate and function symbols, and rho is an environment. That means rho is a function from variables to the underlying set of the structure curly M. So when I call a structure curly M, if I use like the ordinary non-curly capital M, I mean the underlying set of the structure M. So let's maybe just write that down in brackets. Underlying set of M. Okay, so to define the satisfaction relation, we need to basically interpret formulas in the structure. That's what the satisfaction relation means. Now, formulas were built up using, as you will remember from last week, using quantifiers, the propositional connectives and or implies and so on that we had in propositional logic. They built up from those, using those from atomic formulas, which were formulas formed using a predicate symbol, either from the signature or the equality predicate. And those atomic formulas that involve predicate symbols, the arguments to them, the parameters that you give, they were given as terms. And the terms were built up from variables and function symbols. So in order to interpret formulas, before we do that, we first need to interpret terms. So this is in order to define the satisfaction relation. So first we define an interpretation of every term t. So we call this t superscript rho in M for every term t. So the point is that a term is interpreted as an element of the structure, of the underlying set of the structure. So a term, in the case of the natural numbers, if we go above, a term will be something like x plus y, or x plus brackets 1 times y, or 2 times y, or to make it more mathematically interesting, or so on. So these are all interpreted as unsurprisingly, as elements of the underlying set of the structure, the natural numbers in this case. So we want x plus y to mean a natural number. But which natural number it is depends on what the interpretation of x is and what the interpretation of y is. So the point of the environment is to say what the interpretation of x and the interpretation of y is. So to interpret a term, we just need to say how we give a value to every term. Well, the terms were built in a very simple way. They were either variables, or they were built from function symbols applied to terms we already had available, that we'd already constructed. So we just need to say what the interpretation of a variable is. So the interpretation of a variable, according to the environment rho, well, we just define that to be, well, the whole purpose of the environment is to give us the elements of the structure. So each variable we interpret it as an element of the structure. So that's what the purpose of the rho function. So the interpretation of a variable x is just given by the rho function applied to x. And then the other case was when we had a function symbol. The only other way of building a term is by applying a function symbol to the right number of arguments. So this is where k is the arity of the function symbol f. And in this case, well, these were terms we already had given to us, so we can assume we've already got values for those. That's t1 superscript m through to tk superscript m. We've got the right number of arguments here, and so we've got k elements of the underlying set here, given by interpreting these terms in the structure. And the interpretation of the function symbol is simply obtained by applying the function that interprets f, that's f superscript m, to those k values. So this is defined to be the function interpreting f, so the interpretation of f in m applied to the k values we already have from the terms t1 through to tk. And this is where k is the arity of the function symbol f. And having done this, having interpreted terms, we can now define the satisfaction relation. So now we define the satisfaction relation. And the idea is we're going to define, so we want to say what it means to interpret, to say that the formula phi is true in the structure M given the current environment interpreting the variables. So we're going to define this But we're going to do this by lots of different clauses to apply to each different way we have of building the formula phi. So that is, phi could be an atomic formula constructed using a predicate symbol, an atomic formula constructed using equality, or it could be a compound formula built using one of the propositional connectives, or it could be a compound formula built using one of the two quantifiers. Those are all the cases. So let me rub off phi here, and we're going to consider each of the cases in turn. So in the case that we're a predicate symbol, again with k arguments, where k is the arity of the predicate symbol p in this case, well, the point is this holds, this is true, this relation is true, if and only if, well, again, what we have we've got these terms here, so we can interpret those terms as elements of the structure, the underlying set of the structure. And the point is we want this to be true if our interpretation of the predicate P says that the relation P holds for these elements we've got for T1 through to Tk. So here we've got a K tuple of elements from the structure, and we want to say, does the predicate P hold of this K tuple? And it does hold of the K tuple if and only if the relation, the interpretation we've got, the function we've got interpreting the predicate P says that P holds, namely that function evaluates to true. That's the point of evaluating the function to true or false. So this holds if and only if this is true. And again, where K is the arity now of P. Very similarly, if we look at when an equality between two terms is true in the structure M, again we want to say oh, by the way, let me just scroll up a bit. I'm sorry, I'm getting a bit confused here. So it's I'm not really getting confused. I've just written something a bit silly notationally. There's absolutely no reason to have the environment row appearing twice. And the reason I've written it like this is sometimes I write it here and sometimes I write it here. Let's just make one choice rather randomly. Maybe in the textbook it's the other one, or they don't even do it this way, I don't quite remember. But let's make this choice that I'm going to put the row up here. So it's still the same. This says that the formula phi holds in the structure M according to the interpretation row of the environment row assigning elements of the structure to the free variables. So here, here we've got row, and I see I've also been a bit careless here. I'm sorry about that. Right. So this, we want the interpretation of, this is in the structure M, but it's the interpretation of the term given the environment mapping values to free variable, mapping free variables to elements of the structure. And that's essential that we use the environment here because the term might itself be a variable. Okay, so we want to say when it's the case that an equality is true in the structure M under the environment row, and that's simply if and only if and only if the element interpreting T1 in the structure M is equal to the element interpreting T2 in the structure M. And maybe just going back a bit, one might be very strict here and say we're interpreting T according to the environment assigning values to variables, so that we according to that environment row, but actually we're really interpreting it in the structure M. So one might also put a superscript on here. Let's just do that. So this here I missed out. So this is we're interpreting this. I should have put the row here and M here. Okay, so we're correcting things as we go along, and here then and I've made mistakes here as well. Goodness me. I'm not so sharp today, apparently. At least I'm correcting it, but I'm sorry for the confusion along the way. All right. But I want to ease off on the notation a bit, so I'm in particular going to remove this subscript M from now on. So I've now ignoring the subscript M, but keeping the rows. Anyway, so a formula expressing equality is true for the two terms under a given environment interpreting the variables, if and only if the interpretations of those two different terms, they could even be the same term sometimes, but anyway, in general, two different terms under the environments, if those two terms are interpreted as the same element of the structure. So it's what we expect equality to mean, only made very formal, because as it has to be, because we've got this very formal language, namely the language of logic, of predicate logic. So, having done the, having dealt with atomic formulas, we can also define the under what cases formulas involving the propositional logical connectives are true in the structure M under an environment row. So the formula not phi is going to be true in the environment M. Sorry, under the environment row in the structure M. Well, what we do is we look to see whether phi is true in the structure M given the environment row. And if it is, then not phi is going to be false. And if this is not true, then not phi is going to be true. So this should have the opposite meaning to whether, so not phi is satisfied if and only if phi is not satisfied. So we can write that succinctly by like this. Well, that's the satisfaction relation, so let's put a negation symbol through it. That doesn't look very neat, but hopefully maybe let's just neaten it up for the sake of the notes afterwards. But hopefully, anyway, it's clear what I mean. So there we go. So we've negated so this holds, not phi holds if and only if it's not the case that phi is satisfied. The same way, say phi implies psi. We're going to again take the material meaning of implication, in which implication is considered as synonymous with, that's having the same meaning as not phi or psi. So this will hold if and only if either it's not the case that phi is true under environment row, or it is the case that psi is true under the environment row. So we would also deal with conjunction, disjunction, falsity, falsity is never satisfied in the structure. Let's just put dot dot dots for those and go to the more interesting cases, because the the propositional connectives, it's kind of obvious how to deal with them on the right. So let's go to the more interesting cases. So let's think about when a universally quantified formula for all x, or the universally quantified formula for all x phi is true in the structure M under the environment rho, assigning values to variables. Well, of course, for all x phi is going to, the truth or falsity of it does not depend on what value rho assigns to any variable x, to the variable x. Because here we're universally quantifying over x. So the meaning of x inside this formula has nothing to do with rho, but it's rather we're checking to see whether phi holds for every possible instantiation of x in the structure M. So what does that mean? Well, that means that this is going to be true if and only if for every element A in the structure of M, in the underlying set of the structure M, what we want to hold is that phi is true with that value A assigned to x. So we want to say in the structure curly M, phi is true with the value little a assigned to x. So we say that by phi is true in the environment rho, so rho's assigning values to all the variables, except we change the value of rho potentially on the variable x. So this is called updating the environment. We update the environment rho so that x takes the value a. And now we're really checking what we want to check. We want to check that phi is true in the structure M for every possible instantiation of x. So here we've got the quantification over all the a's, all the little a's in the underlying set, and phi needs to be true with x instantiated for each of those. And here we're still using the environment rho because we're still, when we look at variables other than x, then we take their values from the environment rho. So here rho is giving the values to variables other than x, essentially. And for the existential quantifier, it's very similar. So formula there exists x phi is true in the environment rho if and only if there exists some element of the structure such that the formula phi is true in the structure with the variable x updated with its value updated to a. Oops. Okay, try that one again. So it kind of remains to explain this notation. So where rho with x updated to a is the environment that, given a variable, so an environment is a function from variables to elements of the structure M. So given a variable z, it's going to be equal to, the point is, if z is the variable x, then we give it the value a, the environment gives the value a, So if, let's write z is equivalent to x, this means if z is syntactically the same thing, is exactly the same variable as x, and otherwise we go to rho of z if z is not the variable, so let's say not equivalent to, that is, if this means if z is a literally different variable from x. So let me again just make sure that it's clear that that's the negation of the previous. Let me just write, just as a memory jog, syntactically identical. Or actually, maybe a better way to say it, just the same variable. Let's write that. And that is essentially the definition of the satisfaction relation. So it's rather complicated. So this is really a significant way in which first order logic or predicate logic is, which as I said is the same thing, is more complicated in a significant way than propositional logic. So just to say, if we go here, I do have the satisfaction relation written out also in LaTeX on a separate slide. So I shall upload this to the course web page. So here you've got it written out nice and neatly, and it's also got the missing cases in. So let's go back now to the notes. So I just want to make 2 points about the satisfaction relation. So they're rather technical. So the first one is satisfaction depends only on the assignment row makes to free variables. So that can be formulated as a lemma. So if we have 2 environments, rho and rho prime, and they agree, they coincide on the free variables of the formula phi. So this means the set of all free variables in the formula phi. So that's all those variables that occur in phi that are not within the scope of quantifiers. So then it holds that phi is satisfied under the environment rho if and only if phi is satisfied under the environment rho prime. So the intuition here is from these 2 clauses where we see that whether or not the formula for all x phi is satisfied in M whether or not that holds does not depend at all on the value that rho assigns to the variable x, because that value that rho assigns to the variable x gets ignored because the value of x gets updated to all the different a's in the structure. So the original value of rho on the variable x gets ignored. And that's basically the insight as to why the values that are assigned to bound variables in the formula phi are irrelevant to the satisfaction relation, which is what this lemma says. And another lemma is called the substitution lemma, which I'll just, again, it's technical, I'll just write this down and then we'll have finished with such technical things. So then there's also the substitution lemma. And this says that if we consider when we substitute a term t for a free variable x in a formula phi, so that's this notation last week, and we consider whether or not that formula is satisfied under environment rho. Now, of course, this notation means this is no longer exactly the formula phi. It's the formula phi with the free variable, the free occurrences of x replaced by the term t, having beforehand done a little bit of renaming of bound variables to make sure that nothing goes wrong, as we discussed last week. So this is no longer the formula phi here. So how do we decide whether or not this is satisfied? Well, really what we need to do is we need to go through the whole definition of, though this formula now has pretty much the same structure as the original formula phi, only when we get down to the term level, inside the atomic formulas at the bottom, some variables have been replaced by the terms t. So we could sort of unwind all these definitions, and that would be rather long and complicated. The lemma says there's actually a simple formula for working this out, and it's a very intuitive one, which is that this holds, as we would expect, if and only if the formula phi holds in the structure M, but not in the environment rho, but rather the point is we've changed the variable x. We've replaced x by t. So on this side, we use the environment rho, but we change the value of the variable x by updating it to the interpretation of the term t in the environment rho. Okay, so a bit of a technical lemma, but also quite intuitive, hopefully. All right, so as you see, the semantics really is a little bit complicated of first order logic. The satisfaction relation took us a little bit of a while to get through. But now we can define the soundness and completeness theorems. So what I'm going to do, in order to do that, I'm going to make one observation. So from the first lemma above, if phi is a sentence, then the truth or falsity of the relation M satisfies phi, interpreted in the environment rho, is independent of rho. Doesn't matter what environment you use, it makes no difference. Independent of rho. And that's because if phi is a sentence, it has no free variables, and whatever two environments you have, they always agree on no free variables. I mean, if you've got an empty set of free variables, they have to agree on. It doesn't matter what they do on the other variables. So in the case that phi is a sentence, we write simply, so we can just forget the row. So this is, we're going back to what I said earlier on, when we have a sentence, it has a determined truth value in a structure. So we use the satisfaction relation to compute that truth value. Is it true that phi is satisfied in the structure or not? And because because the environment is irrelevant there, then we just have this determined truth value. So why did we need the environment at all? Well, we needed it because of the quantifiers. Because when we interpreted the quantifiers, when we saw whether a quantified formula was satisfied in the structure, we needed to update the environment. And it's clear we're going to need to do something like that, because the point is to go, in order to understand when a quantified formula is true, you need to go inside the formula to look at properties of phi. And as soon as you go inside a quantified formula and you look at phi, you're no longer dealing with sentences. You've now allowed yourself to have free variables. And as you go further inside the formula, you'll get to more quantifiers potentially, and you're going to expose more and more free variables as you go along. So we have to deal with formulas that do have free variables, but in the end, we're really fundamentally interested in sentences and the truth of sentences in structures. And we're going to say that phi is a logical consequence of formulas phi 1 through to phi k, or we're going to even allow ourselves a whole set of formulas. So let's use capital phi. No, let's use capital S. Let S be a set of sentences we say that S entails, I missed an I out there. Now I'm accidentally deleting everything again. S entails phi, or phi is a logical consequence of S. Let's underline the words we're defining. If so, this is going to be like in propositional logic. A formula phi was a logical consequence of some other formulas if phi was true for any assignment of truth values to the propositional atoms that made the other formulas, the formulas that it was to follow from, true. So now we're not just assigning truth values to propositional atoms. Our interpretation is based on having a structure, and every structure gives us essentially a model in which we can say, is the formula true or false? So now our quantification is going to be that phi is a logical consequence of S if for every structure, curly M, for which all the sentences in S hold, then phi also holds. So phi here is also a sentence. Let's put the arrow in the right place. Another sentence. It's not very neat, but anyway, another sentence. So let's write that down. So we want for all structures, so if for every structure M, if m, so if psi is true in M for every psi in S, then let's put brackets, right? I mean, you don't really need them, but so dotted brackets just to make it clear, the logic of the definition clear, then phi is true in the structure M. So in any situation in which all the sentences in S are true, phi is also true. So that's what we would expect by phi being a logical consequence of S. There's no way we can make that if we have everything in S, if everything in S is validated, then phi automatically follows from that. And our notation for logical consequence is S. Again, the same symbol we use for the satisfaction relation, phi. So I think we used this before for propositional logic, but now we're using it in two different ways for predicate logic. Here we're using it as a relation between a set of sentences and a sentence, the entailment relation, and above we're using it as a relation between a structure and a formula, and an environment in this case. So we can always tell which of the, in computer science terminology, we're overloading the symbol, but we can always tell which of the meanings we mean, because it depends on, is this a structure or is it a set of sentences? And the point is going to be about natural deduction that, just as in propositional logic, natural deduction is sound and complete as a way of proving logical entailments. So we write S. So again, using the symbol, the same symbol, turnstile symbol that we used for propositional logic, we write that phi is provable from S if there exists a natural deduction proof of phi with all, let's say, with no open assumptions, and all axioms taken from the set X. No, not X, S. And the theorems are the same as in propositional logic. So again, we have the theorem soundness, and that is if phi is provable from the set S, then phi is indeed a logical consequence of the set S. So it is indeed entailed by S. So once again, just as with propositional logic, that says the rules of natural deduction are correct for predicate logic. We can't, if we can prove something, then it is indeed a logical consequence. We can't do any incorrect reasoning. And in the converse direction, oh, that's because I clicked on the wrong thing. Well, let's give it its proper name. So in the converse direction, we have completeness, but this is called Gödel's completeness theorem, after the very famous Kurt Gödel, who proved this theorem, Gödel's completeness theorem. Completeness theorem. And this is that if a set of sentences S entails a sentence phi, then we actually can prove that. So we have a proof of phi from the set of sentences S, so all of whose axioms come from the set of sentences S. So of course, as many of you will know, Kurt Gödel is very famous for an incompleteness theorem. That is not the opposite of this theorem, because only one of the, because obviously this theorem is true, not its negation. But anyway, Gödel made very major contributions to logic in the 1930s, and this was the first one. This was his PhD dissertation topic, his completeness theorem. It's a very nice result. The proof is beyond the scope of this course, so I won't even talk about it. Maybe the textbook, I think, has a few words about it, but does not go into it in much detail. But still, soundness and completeness are very nice results to have. And once again, we can look at the special case in which we have no axioms, and that says that if we put soundness and completeness together, we can prove a sentence outright from no axioms. So we've discharged all assumptions, we have no open assumptions, and a proof that did not involve any axioms. We can prove the sentence outright if and only if it's entailed by the empty set of sentences. I won't write the empty set here because it'll look a bit too close to phi. And once again, this means so entailing by the empty set of sentences, like in propositional logic. This is saying so phi is valid, logically valid. In propositional logic, we also use the word tautology. One doesn't really use that for predicate logic. Sometimes one does, but it's not normally used. Validity is the standard terminology here. So phi is valid. In other words, simply for all structures M, phi is true. So phi is true in every structure for the same signature. And here we just say phi is provable. So we have a handle on validity because the valid sentences correspond exactly to the sentences that are provable using our natural deduction proof rules. And once again, just to finish the definitions analogously with propositional logic. So validity was important in propositional logic. We were also spending even more time looking at satisfiability. So once again, satisfiability, we say, so as in analogously to propositional logic, let's not write that down. The word analogously is too long at this stage in the lecture. So as for propositional logic, phi is satisfiable. So in propositional logic, it was if we can find a truth assignment to the propositional atoms that makes the sentence true. In this case, it's if there is a structure that satisfies phi. So if there exists an M such that phi is true in M. And as before, we have phi is satisfiable if and only if not phi is not valid. valid if and only if not phi is not satisfiable. Okay, so we've seen that we're in a similar position with predicate logic that we were in with propositional logic. At the moment, it looks very similar. I'm just wondering how to go back. Maybe I'll do it this way. However, what we haven't looked at all are algorithmic aspects yet. We're now in a position to start doing that. So I'm going to do that in the next half of the lecture. Before that, we need a break. So we'll look at the clock on the back wall and have our usual break and meet again in 15 minutes' time. Okay, so bye for now.